Okay, guys, so I think it's recording. Let me check. Recording, sharing. Okay, I think it's good. Okay, so in this video, we're gonna prove this proposition we wrote last time, right? So it says that for any metric space X, the subset phi is open. The empty set is open. Also says that the whole set X is open. I said that any union of any collection of open subsets of X is open, not E, X. And the intersection of finite numbers of open subsets of X is open. Okay, so remember that definition of an open set. A subset S of a metric space X is open if for each P on S contains an open ball of center P. Okay. So for proofs, you can always think in your open sets like that, using the concept of metric, right? So it's not really much difference. Just sometimes need to be careful. But okay, so what we need to prove. Let's do part one. The subset phi is open. So to prove that phi is open, we need to do this definition. If for each element of the set, S contains an open ball of center P. Okay, so we need to say let P belongs to S, to the empty set, right? But because it's the empty set, there is no P. Okay, so there is no such an element P on the empty set. Therefore, so since the statement is false, I can conclude anything. Okay, since the statement is false, I can conclude that the empty set contains an open ball of center P. That the empty set contains an open ball. The empty set contains an open ball of center P. Of center P. Okay, so this is what this is what is called anti-implication. Okay, so that's kind of weird, right? But that's how it goes. Now the subset X is an open set. Okay, so what is an open set? An open set for any element on S, in this case, is the whole space X. For each element of X, S contains an open ball of center P. And so we can say let P belongs to X. So you have let P belongs to X. So let me check how rigorous they want us to be. Okay, so we don't need to do too much here. So This is also kind of trivial statement. So let P belongs to X. Since any ball in E in X is contained in X, then X is open. Okay, so any open ball containing P will be inside of X. Okay, so any ball containing P is inside of X, and this ball exists. Okay, so you can just say because this is a metric space. Okay, so maybe you don't know exactly how it is, but we have a definition of a ball, right? So a ball is, so the set all, let's say the ball of center P and radius R are all the elements X on X such that the distance from P to X is less than R. So this is an open ball, right? And this is an open ball containing the element, the P. And all these elements are from X, so this is a subset of X. So therefore, X is an open set, okay? So this is more interesting. Like these others are like kind of tricky. The union of any collection of open subsets of X is open. So the union of any collection of open subsets of X is open. So let A1, A2, A3, AN be open subsets of X. So let U equals the union of AN n equals 1 to infinity. We will show that U is open. Okay. For that, what do we say? We said let P be an element of U. Okay. So that means so P belongs to the union of the ANs. Oh, this is finite union. Sorry, it's finite union. They put infinity. So let's put K here. K, and N. So P belongs to the union K equals 1 to N. By definition of union, what does it mean? The definition of finite union let me make this K smaller. There exists, let's say K sub 0 such that P belongs to UK0. Okay, so if let's say this is a union, right? So P belongs to the union. So that means P belongs to, let's say, this guy. So, this guy or this guy, okay? So even if it belongs to the intersection or the union, what doesn't matter. He must belong to one of these guys. So this is AK0. Sorry, not UK0, but AK0. Sorry, I have following couple of books, so I kind of missing all the notation. The definition of finite union, there exists K0 says that P belongs to AK0. Okay. And by hypothesis, AK0 is open subset. And this open subset is a subset of the union. Therefore, the union, therefore U is open because the union is U. This is a very typical proof, okay? This is very typical of topology. You are gonna see, we're gonna learn a new concept called compact sets, connected sets. And when you do algebras, there is something called measure theory, and, and you play with algebras. And when you do abstract algebra, these unions, this thing is very typical. Okay, so these unions intersection is very typical tool of mathematics. So it's very important to learn. Okay, so this is open. This is a more traditional. The first two are kind of weird, but it's just a matter of definitions. The number 4, the intersection of finite number of open subsets. Oh, wow. The union of any collection of open subsets. Oh, sorry, it's any union. So the proof is the same. Sorry, this is finite union, and if you have any union, is the same proof. Okay, you do now the union to infinity. Okay, the same set, the same stance, right? You choose a P on the infinity one. Okay, and by definition, it must belong to one of them. So you can have infinite, right? But still, because it's the union, the P must belong to one of them, at least. Okay, and that's the one you take. So you see, this is very interesting because the argument for finite or infinite union is the same. Okay, however, for intersection, and I want you to try this proof, the intersection of a finite number of open subsets of X is open. That one, you need to find a finite intersection. Okay, so let A1, A2, AN a finite collection of open sets. Okay, and let how should we call it, F equals the finite intersection. It's called I equals 1 to n. Okay, let P belongs to this finite intersection. So let's say, so you have this. 3 is enough. Okay, so you this, so P cannot be here because P is in the intersection of all the sets. Okay, so it cannot be here, it cannot be here, it has to be here in this one. because it's in the intersection of the three sets. Okay. So stop the video and try to come out with the open set. Let me pause it here. So I decided what I'm gonna do next. Okay, so better probably, so since this is a final intersection, I just could choose an intersection of two sets. Okay, so sometimes the questions are very general, but sometimes the proof for an easier case is just the same that for a bigger case. Okay, so that's very common. So you can solve an easy case, then you are moving forward. But sometimes you have to verify if you can generalize it. So in this case, let's do that. So let's say we have just A1, A2. Okay. So if you have A1, A2, A1 and A2 are open sets, right? So that means there is a ball for this one, for A1, and there is a ball for A2. Okay. And then, so for each of them, you have a radius, right? So there is a ball of center P and radius R1 containing A1. This is the red one. And there is a ball of center P and radius 2 contains in A2. So what do you think? So we need to find a radius that is contained in both. Okay, so if let's say we have two balls. Okay, no, like this. Okay, see, this is better. Yeah, this is P. This one has radius 1, and there is another one with same center. You see how important it is to draw, because it looks, my drawing are here are kind of wrong. You see, my drawings are wrong here. So this is same center R1. The same center is P, and let's say the other is R2. So this one is R2, and this is R1. So this red one, this red one is this one. Okay. So this draw that I'm doing is wrong, you see, because both balls have the same center P. So that's why this is important to. Sometimes we make a drawing and it's wrong, so this is the case. So that's not right, you know. So the bad thing of not being in class is that you guys cannot say, "Hey, but why?" Hopefully you guys can. You saw something wrong, fishy there. Said, "Oh, by the way, why is he?" So A1. So let me make it big. And A2. The A1 and A2 are open sets, not open balls. Okay. And let's say this is P. So P is a ball. And the other ball could be bigger or smaller, but I went, okay, I said it's smaller, but it doesn't matter. Okay, so question, guys, which ball are you gonna choose? Well, let me. So in this case, it looks like there is no problem to choosing. But what about in my P? Because P is bigger, right? Oh, I like this statement because it breaks your intuition. It forces you to draw. It forces you to draw. So this one, this could be A2. No, it's a ball. So let me make it. So it's a ball. So let's make it like this. You understand me, okay? So you see this red ball is not inside of A2, but the green ball is inside of A1 of A2. So which one are you gonna choose? You choose the smaller radius. We choose if we choose the smaller radius, if we choose the smaller radius, say R equals the minimum between R1 and R2, then the ball concenter P and radius R is inside of the A1 intersection A2, okay? And you know, that's what I want to see, how rigorous we had to be. I mean, it's possible that a faculty will ask you, prove that this is true, okay? And yeah, so maybe you have to prove it. In my case, I'm not going to prove it. The book doesn't also requires to go in detail to prove this, but it's good. So I'm not gonna force it, but some people will ask, okay? So prove that this is true, but you can see it. So you can see it, you can write it, right? Therefore, A1 intersection A2 intersection AN is or contains, well, let me put it here so it's clear. Let's see. I learned how to erase in another way. Let's see. Well, sometimes it doesn't want to erase. Okay. So I want to put it like this. So the ball with center P and radius R is inside of A1 intersection A2 intersection AN if R equals the minimum of the radius R1, R2, Rn. Okay. Where the ball with center P and radius Ri is inside of AI. Okay. So that's something that also probably we will have to show by induction. Okay. So we want to use super rigorous. So, but the book doesn't require it. But so I think it's okay. So we don't need to go so rigorous. It will be nice. It will be nice you do it, okay? It's better for the students. It's better to do it like that. But I'm not gonna push it. It's probably pushing too much. So because this is like an introduction to proofs. So I hope it's clear. So just like I can find a ball for A1 and a ball for A2, but they are centered at the same point. One must be inside of the other one, okay? So in this case, what is going on is you have A1, A2, A3, and A4, right? And each of these have different balls. So maybe one ball is like this, the other ball is like this, the other ball is probably bigger. Okay. Oh, but again, I'm doing the same mistake again because they have to be centered. They have to be centered. Sorry, it's like we always try to always do the same mistakes. Oh, okay. They have to be centered. Okay. Otherwise, it doesn't work. Otherwise, it's more difficult. In this case, that's what this problem is doable at this point. Later, you're gonna have harder questions. But yeah, so basically, there's gonna be one ball, another ball, another ball, but all of that center. Okay, so you choose the one with the smaller radius, and then she's gonna be inside of all the other ones. And since this ball is inside of let's say the ball corresponding to A1, then that ball has to be inside of A1. Okay, and I think that's the proof. Okay, so this is a nice statement. It's a good exercise to practice. So I'll leave you a similar homework with for closed sets. Okay, so I'm gonna give you a homework for that. Okay, so let me stop my time here to see. Let me stop this video here to see what I'm gonna do next.